Next speaker is Keerthi from Infineon Technologies, who is a staff engineer. His topic is formal verification of safety mechanisms. He's based in Germany as a staff engineer and obtained his doctoral degree from TU Kaiserslautern in Germany in 2021. In his current role, he is responsible for formal verification of complex design blocks, formal verification methodology project, and automation of design development flows. Over to you, Keerthi.
Okay, thanks, Mike, for the introduction. Hello, everyone. Today, I'm going to focus on formal verification of safety mechanisms, and I'm going to talk about how to verify formally the error correction codes. And okay, just a second. Okay, so I think when we talk about safety mechanisms, I think it's clear why we use safety mechanisms in our automotive designs. And for anyone who is working in the automotive industry, it's quite clear that ISO 26262, which is the safety body, specifies that designs that are going to be used in safety critical applications need to have some additional functionality to make sure that errors, for example, soft errors and electrical glitches or mechanical glitches can be detected. And also during these conditions, the designs operate with some minimal functionality. And there are different safety mechanisms that are currently used in the industry. And as you see, these are some of the examples: double modular redundancy, triple modular redundancy, ECCs, CRCs, and there are similar safety mechanisms that are typically implemented in the designs. And how they are used, like for example, when to use the ECC or when to use the TMR based on different criteria. For example, depending on the LCL rating of the design and also different design criteria like what the area, performance, power overhead, different safety mechanism is selected for a particular design. And today I want to focus on error correction codes. And in this slide, we have a very brief introduction to error correction codes. Basically, there are two parts to an ECC design. So what you see on the left-hand side of the diagram is an ECC encoder. So the functionality of the ECC encoder is to take the incoming data bits. Before that, these ECC designs, they're typically implemented in the memory regions, like memory interfaces or in the register file interfaces. So whenever the data has to be written to a memory, maybe a program flash or a data flash, the data will be passed through an ECC encoder. And the ECC encoder here, it takes these data bits and computes some additional ECC bits, or some might also say check bits. And the data, together with the check bits, are written to the memory. And let's say after a few thousand clock cycles, the same data needs to be read. And in the meantime, because the chip is operating in an environmentally extreme conditions, and maybe there are photon rays that are falling on this chip, and maybe a bit is flipped from 0 to 1 or 1 to 0. Then we call this as a corrupted data because this was not the data that was written originally. And when this address is read, the same data will be passed through an ECC decoder. And what is the functionality of the ECC decoder? It's basically does the opposite of what the ECC encoder did. So it decodes the encoding, and then it sees or checks if there are any bits that are corrupted. And in cases when the data is corrupted, the correct signals are set here. As you see in this design, up to 3-bit flips can be detected, and 2-bit errors can be corrected. So that's why this design is called double error correction and triple error detection design. So that's the functionality of the ECC decoder. In case when the number of bit errors are within the correctable range, then the data is corrected and then sent out. Otherwise, proper error signaling is done. So now, when we come to formal verification, first of all, we have to think about what should be the formal verification setup. And since we already know that the memories are typically not good for formal verification, we should try to avoid reading in this program flash into our verification setup or formal environment. What we could do, since our main focus is to verify the ECC encoding and decoding, we could implement an RTL wrapper that instantiates only the ECC encoder and the ECC decoder. And what about the bit flips? The bit flips can be assumed through the formal assumptions, as we show here. Okay, so now what I'm going to do is I'm going to talk about 3 different formal verification approaches that we did on this design. So basically, this is a very large ECC design. As you see, the number of incoming data bits are 256 bits wide and 22 bits check bits. So overall, the ECC vector is 278 bits, which is considerably huge. And also, if you look at the capability, the design is able to detect up to 3-bit errors and correct up to 2-bit errors. So the first approach, the formal verification approach, we call it as brute force because we do not do any abstraction. We do not perform any abstraction to reduce the state space for the formal analysis. So here is a property written in system Verilog assertion syntax. And this is one property to check whenever there is a 3-bit error, the correct output signals are set. And as you see in this property, we are checking that the write data and read data. So this is the write data, which is written into the memory, and this is the read data, which is the data read from the memory. And we are counting the number of bit positions in which these 2 vectors differ. And we are assuming that there is a 3-bit error. That means 3-bit positions that differ. And we have to prove whenever this condition occurs, correct signals are set. For example, the error out should be 1, indicating that there has been an error. And also error 1 out and error 2 out should be 0, and then error 3 out should be 1. So that's what this property is being written to. And now, if we think about the analysis space for the formal tool, the tool has to consider all combinations for the data in, and also it has to imitate all the bit errors that could possibly occur in this 278-bit vector. So overall, this is the analysis space for the formal tool to evaluate this property. And as you can imagine, this is quite a huge number. And we ran this property and this design in a commercial formal tool, and the property didn't converge even after 120 hours. So that's the result for the brute force approach for this design. So what we did, we tried to, because at the end of the day, for the safety designs, we want to have a complete proof. And that's why we come up with an approach called divide and conquer. And if you think about the brute force approach, the main problem was this huge state space or analysis space. So we thought, okay, so let's try to divide this problem into a smaller problem. So what we thought was, instead of running the property on the complete 278-bit vector, we could reduce it on a smaller window. And as you see in this property, what we did, we said, let's assume that the bit errors can occur only in the first 16 bits, and the rest of the bits are error-free and also fixed. And this is what you see in these first 2 lines of the property. So here we are assuming that the write data from 256 to 17-bit is error-free, or is even a constant. And also it's the same as the read data. So that means it's error-free in these bit positions. And then we assume that the bit errors, these 3 bit errors can occur only in this small window, and then prove the rest of the output signals. And of course, now the analysis space is much smaller because the tool can only play with these 16 bits, and also the tool can insert the bit flips only in this small window. And the analysis space here is small, and the property converges within reasonable time. But the problem here is, of course, we have to repeat the same property over the complete vector. And also, the main problem is that here we have a verification hole because the ECC has not been exhaustively verified. The reason is, in reality, the bit flip can occur anywhere within this 278-bit vector. And we are only proving a part of a smaller combinations of these all possibilities. So that's why even with this method, even though we get some complete proof, there is still an coverage hole or verification hole. Okay, so then we went to another technique, and we call it as linearity. And here we wanted to perform a complete exhaustive formal analysis. So what we did, we looked into detail of this ECC decoder, and we found out that there is an important part of the design, which is syndrome generator. And so we found out that if we if we found out these important characteristics of the syndrome generator, we might be able to prove exhaustively these ECC designs. And then let's understand what are these important properties, okay? And let's assume the function that is implemented by the syndrome generator, let's call it as syn, and the output of the syndrome generator is syn of out. And now, whenever this write data and read data, they're equal, that means when there are no bit flips, the output of the syndrome generator is always 0. And this can be written as a property and can be proven in a formal tool. And the second important property of the syndrome generator is that it implements a linear operation. So what is a linear operation? So here is the definition. If f of x plus f of y is equal to f of x plus y, then we call such a function as linear function. And if you think about the syndrome generator, it's basically implementing some XOR operation. And here, let's assume x is one of the input vector, some arbitrary input vector, and y is another arbitrary input vector. And we could actually prove this property, which is syndrome of x XOR syndrome of y is equal to syndrome of x XOR y. And in Boolean algebra, we know that XOR operation is nothing but a bitwise addition. So basically, this syndrome generator is implementing a linear function. So what does it tell us? So we proved two important characteristics, which is to say that the syndrome generator is a linear function. And whenever there are no bit flips, the output is always 0. And these two characteristics can be deduced to say that the output of the syndrome generator is independent of the data. So that's one of the basic rule of the linear function, that is independent of the input values. But what does it depend on? It depends only on the bit positions where the bit flip has occurred. So now we still have to prove it. Of course, we have to first prove that the syndrome error free vector property and also linearity property, and then we have to prove this property. And here in this property, we need to add this additional class, which says that basically this is what we proved. We proved with the passing of these two properties, the previous two properties, that the syndrome generator is independent of the input data. So now we can, for this input data, we can assume any arbitrary random vector data, and then we can have the original property here. So now for the same property, the analysis space is almost reduced to 2 to the power 256 times. And this analysis space is quite reasonable for any formal tool, and now the property holds within less than 2 hours. And these are some results. And we have applied the same methodology or the same approach for verifying the ECCs and multiple designs, as you see. And so these are different designs. And in the second column, what we see is the data bits, the size of the data in. And these are the capabilities. So how many bit flips the design can detect and how many bit flips the design can correct. And these are the results with different approaches. As you can see, for large ECCs, the brute force approach doesn't hold up. That means the properties do not converge. Of course, some properties may converge, but overall, the complete property set is not converging. And with the divide and conquer, of course, we have a full proof. That means the property is passing, converging, but we still have a coverage hole there. But with the linearity approach, even for these large ECC designs, we are able to get the proof within reasonable time. For the 256-bit vector design, we were able to get the results in 9 hours. And for the 64-bit ECC design, we get the results in 7 hours. And of course, for smaller ECC designs, even with the brute force approach, it's sufficient. The brute force approach is sufficient. That means we don't need any additional abstraction techniques, but it's still worth to see that there is still some benefits or some gain with respect to runtime that can be seen with the linearity approach. And all our properties runs are captured with the formal tool that we use at OneSpin. And what is the conclusion here for the ECC design is that by exploiting this linear functionality of the syndrome generators, for large ECC designs, we can have property proof runtime much smaller. And in our case, it is at least 50 times better than what we had in the brute force approach. So that's it. Thank you for listening. If there are questions, I'm happy to take them.
Yeah, thank you very much.